vast experience in earthquake field. Sir has a great command on non-linear structural analysis and ductile design of reinforced concrete and steel buildings and bridges. Sir has primary research and development interest in non-linear earthquake behavior of buildings and bridges towards developing displacement-based and energy-based earthquake-resistant design. Sir has authored or co-authored 6 books on earthquake-resistant design and construction. We all are already familiar with Dr. C.V.R. Murthy sir. Sir has given keynote address in inauguration session. So, I would like to request Dr. C.V.R. Murthy sir to grace us with his knowledge on the concept of myths and fallacies of performance design. Over to you, sir.
Thank you, Amira. Just one correction, I am not a doctor. I have not cured any patient so far in my life. That is the only thing I want to clarify before I start. Myths and fallacies. I want to remove one myth. I am not a doctor. And the fallacy is that people keep saying I'm a doctor, but I will not be able to cure people. But yes, we work towards saving people's lives in another way, which is through better design of structures to resist earthquakes. Good morning, everybody. Ladies and gentlemen, welcome to day 3. We are at a point where we have to look a little distant view of what we are doing, and that is why I picked up a subject which is very different today, and that is performance-based design. This word is in the market, and we are looking at umpteen varieties of interpretations of performance-based design. So today we want to remove some of the myths and fallacies in performance-based design. And hence today's discussion will be to begin with about performance-based design, what it is, then the myths and fallacies, and then the road ahead. These are the 3 segments in which I will speak. First of all, to set the context, we are looking at the earthquakes in India causing a number of situations for us which very clearly tell us that there is something that we are doing which is not in keeping with the safety of the people of India. I would like to stop here and then say, what is it in your understanding you would summarize these pictures as? Is this performance acceptable? That is the question that I want to ask from here all the way up to here, and then say, is this performance acceptable to you as teachers of India? So let me stop sharing and ask people to raise their hands and tell me if that performance is acceptable or not. Okay, Lokesh. Mr. Lokesh, which college? You switch on your audio, video, and then speak. If you don't switch on your video, there is no need to ask a question.
Are you able to see me, sir?
Yes, I'm able to see you, Mr. Lokesh. Good morning.
Good morning, sir. Yes, sir. So in the previous sessions, we have seen that.
No, wait. Which college are you from?
Yeah, I am from Miyasi Academy of Architecture, Chennai, sir.
Miyasi, Chennai. So, number okay.
In the previous sessions, we had seen that yes, earthquake, some amount of damage is acceptable because that is going to take away some amount of force. But the images you showed, some of them we see that they look to be fatal. I mean, the one, especially the one where a piece has toppled on vehicles. I mean, those could be fatal for people. So that is definitely not acceptable. But
okay.
a few of them which doesn't cost lives might be fine if it is going to make the overall impact lower by taking off some amount of force.
Yeah, interestingly, all the pictures I showed are not acceptable. And some of them, as you said, are fatal. Some did not cause fatalities, but little more shaking, and it would have come down also. So 225 kilometers away from epicenter, if you're having shear failure of columns, shear failure of walls, then you know that that is not acceptable behavior, right? So then anybody else on? Thank you, Mr. Lokesh.
Thank you, sir.
Someday we will catch up again with you and keep asking questions throughout the short course. And every time you go to any short course, please switch on your video and ask your question.
Yes, sir. Sure.
Thank you. Thank you. Anybody else wants to share a thought?
Sir.
Who is that? Mr. Lokesh, you can lower your hand. Anybody else has a question?
Yes, sir. Done, sir.
Yeah, thank you. Okay, how many of you think that it is not a crime to not ask questions? Nobody. How many of you think it is a crime to ask questions? Nobody. That means most of you are not interested in the lecture. I want you to log out because you're not answering the opposite of the question also. And as faculty members, this is lack of integrity. This is lack of ethical values. And I want you to remember that this is not acceptable conduct. Just as you said, Mr. Lokesh said those buildings, that performance is not acceptable. Even your performance is not acceptable if you don't really answer the question.
Yeah,
Nitin Bhai, Nitin Kataria.
Yes, sir.
हाँ, क्यों आंसर क्यों नहीं करते हैं आप? सो रहे थे? What is this?
नहीं
सुबह सुबह you have to be very sharp. You have to be on your toes.
Yes, sir.
क्या है जिंदगी में और कुछ बचा नहीं है अगर ये नहीं करेंगे तो सीखना
Yes, sir.
बंद. What did अमिताभ बच्चन से? सीखना बंद तो जीना बंद.
Yes, sir.
है ना? आप लोग केबीसी भी नहीं देखते हो, वो देखोगे तो कुछ सीख जाओगे. संकेत जैन साहब.
unmute कीजिए please.
Good morning.
See, I love people to switch on their videos because then it shows seriousness of their participation in the program. Bandwidth नहीं है, bandwidth को मारो गोली, है ना? Do everything to make sure you have bandwidth. जिंदगी का bandwidth खत्म हो जाएगा अगर आप वीडियो ऑफ कर दोगे तो. Good morning, Madam Rawal.
Please unmute.
Morning, sir.
ma'am.
Morning, sir.
Morning, ma'am. Morning, ma'am. I know I'm being a little aggressive, but performance-based design is a very aggressive subject. So I hope you understand.
Yes.
I'm asking a serious question, whether you want to save lives or not. That is the question I'm asking. Okay, let me take it forward from here. Keep your videos on. And so you can see the picture now?
Yes, sir.
Yes, sir.
Yes, sir. Yeah, so it is a cycle stand that has collapsed. So that with no college teaching the subject of earthquake safety in the country, even cycle stands will fall. This is the simplest structure we teach in structural dynamics with one mass and one vertical pair of columns. If we can't design this, if we can't do the calculation right for this, and if our students graduate and they can't make one simple cycle stand there, then it is not something that we need to rest on our backs. This is a serious matter of all the faculty members failing in the country to teach the simplest structure, how to design and make it stand vertically upwards. Answer is in front of you. And so I would like to go to the next question here. In 2010, Canterbury in New Zealand had an earthquake, and in that they had a lot of collapses again. But this time, Canterbury said that we don't want any more collapses in any future earthquakes. So they brought down 1,400 tall buildings above 15 stories tall, and then decided that they will rebuild that whole place, the main downtown area. Right? And right now they built only low-rise structures because they're doing a serious study on how to design buildings without damage in the years ahead when there's a bad earthquake again repeating, how to design buildings so that the collapses that they saw in 2010 don't recur again. And so Canterbury earthquake is an occasion, it's a watershed in the world where in a city is saying we don't want any more damages. So what has happened in 1900s, early 1900s, there was loss of life everywhere in the world. Today, many countries have dropped loss of life through diligent earthquake resistant design. But there are still some countries, even New Zealand has done very well, but some of these older structures are taking a beating now. But they want to now make sure that only those structures are built which do not have damage in them. So they are doing serious study, and I'm hoping that they will lead the subject from the front and we will have something to learn from. Having said that, it is time for us to understand what is performance-based design. They thought that that performance is not acceptable for them. But we have to understand what is performance-based design. It is interpreted in different ways by different people. And so it's necessary for us to go in deeper into the subject here. So the first thing I want to do is recall the 7 virtues of earthquake resistant structures, which are good configuration, adequate initial stiffness, sufficient lateral strength, adequate ductility, reasonable deformability, desirable collapse mechanism, and energy dissipation in the structure. This is where we are talking about the 7 virtues. If they are satisfied, we will be able to make an earthquake resistant structure. The question is, this energy dissipation, should it be through damage of structural elements or through damage in select elements like base isolators or energy dissipation devices without damaging the structural elements, so that they can quickly replace that and come back quickly into action again. So what we are looking at, these 7 items that we talk about, the 7 virtues that we talk about, each of these virtues has a physical meaning for us in the world of performance. Configuration will decide undesirable behavior of the structure will be captured by configuration. If you have undesirable behavior, then the configuration is incorrect. If you have damage to non-structural elements under small earthquakes, then the stiffness is insufficient. If you have damage to structural elements beyond what is actually conceived, then you say the strength is insufficient. If there is rupture in structural elements, then you would say ductility is not available in the structure. If collapse of the structure is happening, then you say there is not enough deformability of the structure. And if the type of collapse is brittle or localized, then you say the desirable collapse mechanism is not accepted. Now somebody says, no, I'll fix all of these. I'll give you a good behavior of the structure, no damage to structural elements under small shaking, and there will be acceptable level of structural damage in structural elements, and that rupture of structural elements will not happen, and that collapse of structures, if they have to happen, they will happen in a ductile way, and the mode of collapse is accepted. Excellent. Then the last question is, what is energy here? Energy has to do with 2 things. One is post-earthquake shaking duration is one, and second is the aftershocks that will come into the picture. Both of these, if the structure has to resist, then we need to have the energy absorption understood very deeply. Let's go into each of them. Performance-based design. Level 1 is configuration, undesirable behavior of structures. All of us have seen that the open ground story structures are a disaster, and the Indian Oil Corporation general manager said, I don't like this anymore, and he arranged to fill the lower story also with walls and made additional apartments of smaller size though in the lower stories. This is something that came out of experience, and the general manager, even though he lost his wife and daughter in the earthquake, managed to think for others, and he is the true son of India, in my eyes, the true hero after the earthquake. Second is performance-based design in stiffness. Level 2 is stiffness. We talk about non-structural elements collapsing here. And non-structural elements will collapse under lower shaking because they were not properly jointed, they were not properly held to the structural elements, and so their inertia is not getting transferred to the structural elements swiftly. So damage to non-structural elements is not acceptable at low levels of shaking. We're talking damage to structural elements. Here is a structural wall that undergoes shear failure. Shear failure is not acceptable in structural walls. Even though the structural wall by its mere presence and area has prevented the collapse of the structure, it is that the member has to do a lot more energy dissipation. So if it was failing in a ductile way, then you would say that the damage to the structural elements is acceptable damage. If you're looking at rupture in structural elements, this is definitely not acceptable, where the transverse hoops will open up and the shear failure will happen in the column. This is not the acceptable method of failure of any RC member here. So ductility is not going to be available if members fail in a brittle manner here. Deformability, overall deformability of the structure will lead to collapse. If the structure has to swing back and forth under small swing, if the structure will collapse, then you will say that it doesn't have sufficient deformability. So lateral deformation under inelastic actions has to be reasonably large for it to withstand the shaking during earthquakes. Desirable collapse mechanism is something that we need to understand before we release the design for construction. Open ground story structure, tall lower story structures, slender upper story columns due to extensions, miserly extensions, or an intermediate story with all the infill walls removed and glass caging there for excellent view of the valley. All these are not acceptable collapse mechanisms. And what we require is something straightforward and simple, where every citizen of India is working for the development of India. Every member there is getting into inelastic action. And when I say every member, every identified member, which is the beam, has to come in and participate in flexural, ductile, inelastic actions to absorb energy and thereby create large lateral deformation capacity of the structure. And the seventh item is actually post-earthquake shaking duration. The top left picture is the accelerogram, and the left bottom picture is the energy that is fed by the earthquake to the structure, and that you will see is about 35 joules per kg mass of the structure. But what the structure is able to take is only about 14 joules per kg of the mass of the structure. And that means there is still a large amount of energy which will go begging, and that is where the trouble is for us, that the structure doesn't have the capacity to absorb large amounts of energy. This is what we have to address in the seventh level of performance-based design. So this is all of it together, and in this picture we are only talking about structural performance. In fact, this lecture is only about structural performance. There are other performance like cost of the structure, like downtime of the structure, like the economic impact of the collapse of structures and business downtime and business losses and so on. I am not going to address those in this lecture, but I would like to mention here that I will just demonstrate in this lecture the collapse of the structure, how to prevent the collapse of the structure, how to do performance-based design to prevent collapse of the structure. While there is a detail for each of the remaining 6 also, I will refrain from doing that, but today I will spend attention only on how to prevent collapse of the structure so that you will be able to understand that. Now, what is the philosophy of performance-based design? Before I give the answer, I want you to give me the answer. So I will stop here and say, what should be the philosophy of performance-based design? Can anybody answer this question? What should be the philosophy of performance-based design?
Structure
What?
should behave at that
Nitin,
the we are the desired level.
Nitin, is your video on?
No, sir, the camera is problem there. I'm just logging with the
Oh, go
laptop
to the
now.
shop. Go to the shop and buy a camera.
Yeah, just a minute, sir.
Anybody else? As Nitin is going to the shop to buy the camera, can somebody else raise a thought? What should be the philosophy of how do we do performance? In the simplest words, what is performance-based design? That is what I want to ask. Okay. So since this is your first lecture, you may not be at ease to answer that question. So let me pose that question to you with this set of visuals. We know what is our material that we're using in construction. We know how to do section design. We know how to do member design. We know detailing, but we don't know what is the likely outcome of our design in the form of the lateral response of the structure and the collapse mechanism of the structure. Today we are doing only the forward loop, but not the reverse loop. So performance-based design means do the reverse loop also and know the performance of the structure before you construct the structure. That is performance-based design. There is no magic. There is unnecessarily large number of railway station coolies trying to take you to different hotels when government has already given you a rest house. That is the story here of performance-based design. It is simply you have to do hard work. Now, what is the reason why this reverse loop is not happening? One, we are not teaching nonlinear analysis. Second, computer programs sold in the market are expensive and we are not willing to buy them at 5-6 lakhs of rupees. Personally, we may not be able to buy them, but as an institute, we should push towards buying the basic software that is required if you really want to save the people of India. Okay, so I request you to request your institute or university to buy the nonlinear analysis software. Until such time you know what is happening at the back end of nonlinear analysis, at least use the front end of nonlinear analysis with the help of commercial software, and eventually when you start asking questions, then you will go to the back end and understand what is nonlinear analysis. At this juncture, I must also mention that as teachers, you have to do new things in 35 years of your career. One of the new things you have to do is not to teach the same linear analysis over and over again, but to start teaching non-linear analysis. If you really want to save people, please teach non-linear analysis. If you don't do that, then you're not being honest to the cause of saving the lives of the people of India. Right. So you must have seen this picture in Professor Rupan Goswami's, you have seen the slide in Professor Rupan Goswami's lecture where he's talking about the elastic maximum force divided by response reduction factor, giving you the strength design force, and then a fraction of that becomes the deformation serviceability design force level. And based on that, we look at whether the deformations are acceptable or not. Today, we will go forward the remaining 4 items that he had shown in his lecture, which is minor shaking, moderate shaking, severe shaking, and I'll add one more, which is the extreme shaking. Okay, let me explain each of these one by one to you. Earthquake resistant design philosophy, classical design philosophy for building says that under minor shaking, there should be no damage in the structure. Under moderate shaking, no significant structural damage. And under severe shaking, there should be no collapse. And so it is defining 3 levels of earthquake shaking and is asking 3 levels of earthquake performance. Under different levels, the performance expectation is different. Interestingly, it is only a qualitative statement. Our responsibility when we start designing structures is how to convert this qualitative statement into quantitative statement. This qualitative statement is about 60 years old. And after 30 years of the statement being made, the first effort of quantifying the 3 performance levels started in the late 80s. And that is where that was the beginning of performance-based design. And the question is, at severe level of shaking, it will not collapse, but at what level of shaking will it collapse? So there must be another 4th level, slightly higher level of intensity of shaking, and that is where the game of quantitative behavior comes into picture, and that is called extreme level of shaking. And here, that is the level of shaking at which collapse will happen in the structure. So the original earthquake resistant design philosophy is on the left hand side with a qualitative statement, but now by defining the extreme level of shaking, we should be able to say this is the level of shaking at which the structure will collapse. So given a structure, you know all the material, geometry and boundary conditions of that structure, you should be able to estimate quantitatively what is the fourth level of shaking at which the building will fall down. As of now, the Indian standard is focusing on level 3, which is no collapse is the only statement that we are making, but we are not guaranteeing in the design procedure that if you design by the Indian standard that it will not collapse, because there is no quantitative procedure to assure you that. The only way you can assure that there will be no collapse is actually going back to this reverse loop and making a closed loop design. That's the only way we can do that, because people use different geometries of structures, different plan shapes, different vertical elevation, stiffness changes, mass changes, strength changes. It is not possible to codify all of it. It is the responsibility of the designer, and before that, it is the responsibility of the teacher to teach the students how to assure the client that the building is actually safe and will withstand the level of shaking. Right? So this is the beginning of the performance-based design story, where we are talking about no collapse at severe level of shaking, but there should be a shaking level called extreme shaking, and at which collapse will happen, and we have to quantitatively identify that. So that is where all the 4 levels that you're talking about, minor, moderate, severe, and extreme, come into picture. You will notice here that these 4 levels have nothing to do with the strength design and serviceability design, which are done at a much lower level. As you can also see, at this level of strength and serviceability design, it's a linear behavior, and that is why you're allowed to do linear analysis. That is the reason why you're allowed to do linear analysis, because we obtain the strength design quantity as per the previous picture. The strength design quantity, the lateral force, design lateral force, is obtained using the severe level of shaking, but elastic behavior, and divide that elastic force with R, and you will get to the strength design. So this is where the magic is, that you need to recognize that we are looking at is moderate, minor, severe, extreme as performance evaluation ground shaking levels, and strength design and serviceability design are distinctly different levels or forces or at which those calculations have to be done for the purposes of design of the structure. So if I can say that the first 2, strength design and serviceability design, are design level issues, and all these 4 levels of shaking are performance evaluation issues, that will be the starting point for this discussion. Right? So there is one structure and 4 levels of shaking and 4 performance expectations. Now, what is the 4 performance expectations? At the minor level of shaking, the item in focus is stiffness. At the moderate, the item in focus is strength. At the severe, the item in focus is ductility. And at the extreme, the item in focus is deformability. And therefore, you need to have a design procedure which estimates all the 4 quantities before the structure is designed and built. And so analytically, we should be able to satisfy ourselves that, yes, I know the deformability of the structure and it will collapse at a level much larger than the severe shaking level. And I must mention here, Professor Rupen Goswami has done it, but I will also say that once more, earthquake is not a force, earthquake is displacement. And that is why you're seeing me show all of these arrows for stiffness, strength, ductility, and deformity going from the bottom side, which is the x-axis, which is the deformation axis. Let me write it in front of you so that you'll remember for the rest of your life. I deliberately did not write it at home. I will write it now for you, and I will say deformation. What is deformation? Deformation is relative movement between 2 parts of a structure. In the case of a building, this diagram is drawn by the relative movement between the bottom and the top of the structure, which is roof of the structure. And this is force, which is lateral force in this case, because we're talking about lateral deformation and lateral force, right? So please recognize once more that earthquake is displacement loading, and we are interested in making the structure safe against displacement actions imposed, the inertia forces induced under displacement load. Okay. What is the analytical tool that we use? Classically, all these diagrams that I'm showing you are drawn with the help of a nonlinear static pushover analysis. So what is pushover analysis? You take the structure and push it over till it falls down, and you have to do this analytically. That is our game, right? The question is that where do we stop these four levels: stiffness, strength, ductility, and deformability? We need to find quantitatively what are these levels at which we can say that the behavior is acceptable. So now for reinforced concrete structures, we identified four performance levels based on actual behavior of the members in the structure. What is this here? The first level says the first yielding of the steel bar will be the point where the nonlinear behavior starts. So below that, there will be no structural damage. The second one says the first spalling of the cover concrete happens on the compression side, and we say that is minor structural damage. Spalling of cover concrete is considered minor structural damage. But if the cover concretes of all the members spall and there is the last spalling of cover concrete on the compression side, that is now identified as the severe structural damage state. So what do you have? You have only the reinforcement cage and the concrete inside that. Nothing has happened to the concrete inside that. Only the outside concrete has come off. The cover concrete has come off. And this is the reason why you have to be very careful when you choose very small cross sections, beams or columns. If the cover concrete accounts for 60% of the total area, then you are in deep trouble. If you take a 10-inch column or a 9-inch column, 9-inch by 9-inch column, and if you put 40 mm cover on all sides, go to the center of bar of a 20 mm, you reach 50 millimeters, you lose on all sides, right? So instead of being 230 by 230, it will become 130 by 130. And those of you who have a calculator can quickly run 130 by 130, and I'm doing it with you. And 130 by 130 divided by 230 by 230, and that is giving me 32%. So core concrete is only 32%. So on earth, don't ever make such silly column sizes that 70% of your concrete is actually cover concrete. That will be a very brittle structure. You don't want to lose 70% of a column. The structure won't stand after that. So this is severe structural damage. The last item is first crushing of the core concrete. First crushing of the core concrete, and this is called extreme structural damage. Once the core concrete crushes, concrete reaches its ultimate strain, then it is over and the structure will collapse. So this is the sequence of trying to map those four levels. What are the limits for minor, moderate, severe, and extreme shaking? And that is the reason why in reinforced concrete, we are able to establish this with the help of these four performance states. Just to show you some examples, a normal 5-story building, regular grid, regular geometry, R equal to 10, 8, and 6. And we design structures for 0.1 G to 1 G at every 0.1 G increment. And column bases are fixed and hinge. I'll show you only fixed base column solutions. Now we do the pushover analysis, we get the backbone curves. You can see the blue curves are all first yielding, when the first yielding is happening. The green is where the first spalling of the cover concrete is happening. The orange is where the last spalling of the cover concrete is happening, and the red is first crushing. Red will be only 1 point. Red is first crushing of the core concrete, and then the structure stops, right? So you can see R equal to 6 versus R equal to 10. What is the difference here? What is the difference? R equal to 6 versus R equal to 10. The stiffness is higher in the case of R equal to 6, and the stiffness will get lesser and lesser as you go, because you can reduce the lateral force, you will reduce the member sizes also. But let's go to the more interesting part. How much acceleration can it resist? Because you are interested in acceleration, I'll go with you for a while. These are the four levels: minor, moderate, severe, and extreme. At what level of acceleration the minor is getting started, and at what level of acceleration input the moderate, severe and extreme are getting activated. As you can see here, that since we have designed for the severe level, that will go as a straight line, and you are able to quantify where minor is, where moderate is, and where severe and extreme are. This is the gap between extreme and severe is actually the reserve deformation capacity that we have in our structure. But here is the axis of load, but we have to do the same graph for deformation. Now, based on that, generally we have understood that if you design for a certain level of force, then the minor is twice the level of the force, and the moderate, severe, and extreme are 2.5 times that one. 2.5 is about the overstrength. If you design structures by the Indian codes, you won't get more than 2.5. Around 2.5 is what you're getting, little up, little down. But on the horizontal axis, if you have designed for a displacement of 1, the minor will be at 2, moderate will be at 4, severe will be at R, and extreme will be at 1.25 R. This is what we have understood when we design these structures for the different levels of shaking. So in effect, what is happening is that you are able to see exactly what is the consequence of your design. If you design for low level of forces, you will get a very weak structure and it may not go all the way to the end. So let's take a look at this. So choosing the desired performance level for each structure type and designing it accordingly. I've taken 4 structures here. Understandably, structure A has got more strength. I've used larger strength for A, lesser for B, even lesser for C, and much lesser for D. Now, what is the story here? If there's an earthquake which is imposing this much of lateral deformation, what happens? Structure D is collapsing. That means very small strength is not acceptable. That is why Indian standard has a minimum lateral base shear to be used in the design. So that is to avoid D. Now, case C is where normal buildings are, will get into inelastic, large inelastic actions, but no collapse will happen. Case B is where you want only nominal structural damage because these are critical important structures. These are important structures like the hospital, which we wanted to be functional after an earthquake. And then there is another building A, which is a critical building, the national security issue here. Something very, very confidential is happening in that. And so we don't want that structure to have any disruption because we need those people and need those activities to go on despite an earthquake. And that is A. A is fully elastic when this earthquake is come. B has got into small and nonlinearities. C is large nonlinearities. D is already collapsed. So in effect, one of the simplest ways for coming up with improved performance is by using higher design force. So any designer who is trying to miserly reduce the design force to the lowest is actually going from A to D and not really saving the people's lives, but actually putting them in jeopardy by exploiting the loopholes of the standards and doing some calculations and showing on paper that it is okay. Now, once again, earthquake is displacement loading, and I pray that you understand all the 4 waves and that P and S are the most damaging, but love waves are equally rattling the structures, especially along at the surface of the earth. Now, the game is earthquake is displacement loading. We need a displacement response spectrum, SD, to be used, and that is not available in the Indian standard. You can say, no, I have acceleration response spectrum. Can I not convert from that? You can, theoretically, yes, but in practice, we have not managed to record displacement so far in the country or even worldwide in a significant way to come up statistically that this is the displacement response spectrum confirmed for this region. So the day we are able to put enough displacement meters in the country, we will be able to come up with displacement spectrum. Then we don't have to go through the wrong route of acceleration. You will go through directly through the route of displacement, and that will be called displacement based design. As of now, since we don't have a reliable displacement spectrum, the reason is that the ground motions are being filtered, they are being corrected, and in the process of correction, they are also dropping away the actual displacement slip that is happening at the fault. And that is the reason why displacement response spectrum is the future of good design for earthquake resistance, because earthquake is displacement loading. Now, as of now, we're doing acceleration. So there is a place and it has got a maximum acceleration of 0.8 g. It's called the maximum credible earthquake. But we don't design all structures for that. We take buildings and we design those normal buildings for a value much smaller, and we call that as maximum considered earthquake. And for, let us say, important structures like hospitals, we slightly increase that value, the maximum considered. And for critical structures like transport, water, power, communication, gas related, we raise it even higher. And for special structures like dams and NPPs, we have to go close to the truth. And the question is, how truthful is this truth? 0.8 G. We'll learn that in a minute. Now, just to get you that, if you have seen on the y-axis is probability. If you want to take chances, no chances, you will design for 0.8 G. If you want to take full 100% chance, don't design. That means earthquake will come and you can have the structure collapsed and people will die. That is not acceptable. But typically what is done is structures that are built in large numbers, that is normal buildings, they are more chance is taken in them than those special structures which have second order disaster likelihoods, and so there no chance is taken. In between, of course, there are gray shades here. So this probability is related to two quantities. One is the reference number of years in which there is a likelihood of the earthquake happening again, and that is called the return period, and that is what you're seeing on the last column on the right hand side, the return period. And the probability of exceedance during the reference number of years is 50%. If you take 50% chance, you need to use a return period of 73 to be able to design structures. You want to use 20% and 225 years, 10%, 475. And this is what we are noticing, that when you do all these different ground motions, you are actually choosing a certain percentage, and that is what is giving you different return periods. Over the years, general understanding is small intensity events are frequent, and we will have a small return period for them. They keep coming regularly. Large intensity events are rare and they have a large return period. So when you look at the right hand side column and look at the return periods, they're very large. That means you're taking a very small probability of exceedance. You don't want your special structures, dams and nuclear power plants to go through any damage, because it's difficult to contain the consequences of any damage in that structure. And that is why it is 0.5% is the probability. While in normal buildings designed for severe level of shaking, 10% probability is accepted. For important buildings, 5%. For lifeline buildings, 2%. And for special structures, design is done at 1%. Okay, this return period does not mean that the actual earthquake will return in so many years. No, that's not true. This is a mathematical construct. This is how we have learned to prioritize the design force level, relative design force level, and we are using this approach to give the relative values for different structures. Nobody can say that in buildings that the earthquake will come back in 475 years. No, it can come back in 30 years. Like in Bhuj, 1956, there was an earthquake in Anjar, and then 2001, there's an earthquake. Where is 475 years? Right? It has come back earlier than that. And so we would say that we definitely don't have the physical return period of the earthquake related to this quantity. This is a mathematical way of interpreting the severity of the earthquake. Okay. So the reference period here, duration is taken as 50 years, and we design normal structures for 475 years and important structures for 975 and critical for 2475 and special for 4975 and NPPs for 9975. Now, this is what we have generally stated. Now, special bodies like the Central Water Commission looking at dams or the Atomic Energy Regulatory Board looking at nuclear power plants can say, no, no, we want to use a slightly different number. That's perfectly fine. They will go with higher numbers usually, and so that's also fine with us, not a worry for us. Because those are to be done from multi-dimensional point of view. So normally 4 and 5, we don't discuss these structure types 4 and 5 in public. Normally we will discuss 1, 2 and 3 only. So let's talk about 1, 2 and 3. The first minor level of shaking is where non-structural elements are in focus and you're looking at deformation, stiffness as an issue, and deflection, crack width and vibration is the focus. Second one is moderate, where we're talking about P, V, M and T, axial force, bending moment, shear force, torsional capacities, and strength is coming into picture here. At the third level, severe level is where we do the design. We are relying on ductility here. We're talking about material limits like curvatures and strains. And finally, the extreme level of shaking is plastic lateral stability. We're talking about deformability of the structure to be addressed here. So these are all the 4 checks that we'll have to do. So we will design by the original procedure. But when it comes to taking that structure designed by the original procedure and then put them through the minor, moderate, severe, extreme shaking, the quantities that we will watch are these quantities. Deflection, crack width, vibration at minor shaking, axial force, shear force, bending moment, torsional capacities under moderate shaking, material limits. So the curvatures have reached large values, or the strains in the materials have reached large values. That is the focus. In ductility in the severe level of shaking, and finally collapse of the structure is plastic lateral stability in the collapse mechanism and so on. Whether the deformation demand and deformation capacity are giving us the correct answer. Another important point is we don't design earthquakes for magnitudes of the earthquake. For example, a magnitude 8 earthquake happening in Los Angeles diametrically below India on the other side of the globe is not going to do anything in India. A magnitude 8 in Italy also is not going to do anything in India. Magnitude 8 in Indonesia is not going to do anything to India. But of course, I'm not talking about tsunamis, but non-tsunami shaking, ground shaking alone. What we then design for is actually what is the shaking under the ground at the location I am standing. And so the quantity there is not magnitude of the earthquake, but intensity of shaking created by the earthquake. And so if you look at intensity of shaking based on past earthquakes, intensity is measured 1964 MSK scale in Roman capital letters. If 9 is the intensity corresponding to seismic zone 5 here for us, we are expecting a peak ground acceleration of 0.65 G to 1.25 G. Now, if you look at the numbers correspondingly in seismic zone 4, it will be 0.35 to 0.65. In seismic zone 3, it will be 0.3 to 0.35. And seismic zone 2, it will be 0.1 to 0.2 G. Right? Now, if you recall, in Ahmedabad, we got a 0.15 G or so shaking, and we had 14 how many? 800 buildings collapsing in Ahmedabad city alone, 730 or some buildings collapsing, including 2 11-story buildings. Right? So that is not acceptable that at this level of shaking, our buildings are collapsing. That is not acceptable. That means something is amiss here. Now look at what we did. Here, international literature is saying intensity 9, we're expecting 0.65 to 1.25 G, and India is designing for 0.36 G. We are underestimating hazard by a factor of 3. And that is the worry that we have, that we need to correct that urgently. Otherwise, we will see more collapses and more losses of lives in the road ahead. This is a serious matter for us, and work is underway to revise the Indian seismic zone map. So the 2 questions that come to my mind is that I have a structure designed for the effects of seismic zone 5 with Z equal to 0.36 G. Question is, will it withstand the earthquake in seismic zone 4 with which has a Z of 0.24 G? And the second question is, I've designed it for seismic zone 4. Will it withstand the earthquake in seismic zone 5? That is the question. So let me pause for a minute and ask for inputs from colleagues. Who would like to answer now? Is the question clear? I have a building designed in seismic zone 4 and it will be put to shaking of seismic zone 5. Can it withstand? And vice versa. It's designed for seismic zone 5. Will it be safe in seismic zone 4? I have one hand raised and that hand raised, and the winner is, who's the winner? Sanket Jain.
Yes, sir. Sir, if we design for seismic zone 5, I think it will stand in seismic zone 4 also.
And the reverse question, if you're designed for seismic zone 4, will it stand in seismic zone 5?
Sir, it may stand, but
No, May, June, July are not allowed. Give me precise answer. May,
sir,
June, July.
yes, sir. Sir, it will not collapse, but
No emotions. Fact. 0, 1.
Sir, no, sir. It
No.
will not.
Okay.
Yes, sir.
Let's hear from others. Let's hear from others. भारती साहब बाद में आएंगे. भारती साहब फाउल आप अभी नहीं आंसर बता देंगे. थोड़ा सुनते हैं, सबको सुनते हैं. Nitin Kataria.
It is also depend on the soil condition also, where we are considering it is zone 4 or zone 5. It depends on that.
By the way, I have given the answer already in the preceding part of my lecture. I have already given the answer. So that is why I was looking for whether you are able to relate that part to this. Soil है, ground shaking है, वो सब है, but कुछ और, एक और बात थी. असली बात, मोटी बात, big ticket item. And that is why I raised that question. Anybody wants to answer?
Like you have told that ABCD type of structure, in that one category of structure that we depends.
Depends on category of structure, depends on the type of soil.
Yes.
Let us wait. Let us see if there are some more thoughts. Let us see if there are some more thoughts. Anybody else wants to answer? Hey, return your salary today if you don't ask question. Tell the principal I'm returning my salary today because I didn't ask question. If you haven't asked a question, if you have not learned anything, then return salary. I guarantee every day to myself, I have to learn something and I have to be useful to somebody. Both, then only I'm, going to go back home happy. And when I sleep, it takes less than 1 minute to sleep. Okay, anybody else? भारती साहब से पूछते हैं. भारती साहब, 5,000 रुपए के लिए पहला प्रश्न. You're muted.
See, it will not, because the current design practice gives you the force demand. I mean, it doesn't tell you about the displacement demand. So now both the things are unguaranteed.
Both are unguaranteed.
It will.
Yeah. Yes. So the key question is earthquake is displacement loading, and we are not checking whether it has that deformation capacity. So as of now, Prabhu ki ichha. Seismic design will be Prabhu ki ichha. If you don't do displacement check, if you don't do the reverse loop, then we are not guaranteeing safety. Seismic is 0.36 G. It's 1/3 of what it is likely to be, or even 1/2 of what it is likely to be. On one side, the acceleration levels are itself wrong. On the other side, we are not focusing on asli issue. The real issue is earthquake is displacement loading. What is the displacement capacity? Hai na? So this is what we have to do to make sure that we understand performance-based design. So let me go back to performance-based design. So I hope the answers to the two questions are clear to you. No guarantees in life. If you do the current procedure of design, no guarantees in life. Okay, so to ensure that this is what is the earthquake resistant design philosophy in textual matters. Minor and frequent earthquakes, no damage. Moderate earthquake shaking, no or minor damage to structural elements, some damage to non-structural elements, and severe and infrequent earthquake shaking is damage to structural elements, but without collapse. That is what is the game. How do you guarantee without collapse? So if you look at some international documents, so you will say that this man is not telling me anything about foreign countries. So I will give you foreign country, one item only in foreign country. SEOC means Structural Engineers Association of California. This is America. They came up with a document which talks about 4 levels of shaking and 4 performance levels: operational, occupable, life safe, and near collapse, and 3 performance objectives, which is the combinations of these. They'll say this is not acceptable, this is the basic requirement, this is essential, and this is critical. That is how they have summarized those in this here. So what they're saying is, if you have a frequent earthquake, it should be operational. So they don't talk about issues like occupiable, whether it's occupiable or not, whether it's life safe or not, whether it will collapse or not. That's not a discussion at all. Under basic earthquake level 1, frequent earthquakes, it has to be operational. Under occasional earthquake, what they're saying is the essential requirement is that it has to be operational, and the under a rare earthquake, only they'll say safety is a matter to be examined under rare earthquake. Under very rare earthquake, for normal buildings, they are not giving us any scope for discussion here. Okay, so this is how they are specifying. Again, this is qualitative, right? There are no quantitative statements made in here. But what they do is, these qualitative statements are design objectives, but designers don't know how to convert this. So unclear how to meet these expectations or implement these design objectives. Then a little later, they went through the route of the probability of design, and then they quantified the 4 levels, and they said 10% probability of exceedance in 50 years is 475 years. 2% probability of exceedance in 50 years is 2475 years. So this is how they came up with quantifying the level of earthquake. So out of the 3 items that you saw there on this previous picture, here levels of shaking, performance levels, and performance objectives. The first one they managed to quantify, but the second and third is still a game. So let's see what they have done in the second and third. So this is how the hazard level, they gave a map for that. So 475-year return period map is on the left side, and 2475 return period map is on the right hand side. Obviously, you will see that it will get higher levels of shaking will come if you are looking at the larger return periods. For example, in California, you will talk about 0.8 G as the design along the San Andreas fault, the red line that you are seeing. Okay, now the question then is performance objectives. How do you design? They said, okay, for earthquake level 1, you design with a normal reduction factor, with no reduction factor of just 1. And for earthquake level 2, you design with 0.5 R as reduction factor. For earthquake level 3, you design with 1 R as the reduction factor. And for earthquake level 4, they said use 1.5 R as the design factor, reduction factor. So they're trying to mimic the design procedure to match those 4 levels. That is the second one they did, right? So you remember just now we talked about behavior of concrete structures with these 4 behavioral states. What this CEOC document said was it has to be operational. Operational, we are now correlating with this first yielding happening. And so we have a quantitative way of trying to look at performance now. They don't have that yet. This is something that we did in India. So we are able to now give a quantitative limit. If you have to be occupiable, then we're saying minor structural damage, the first spalling only has happened. Occupiable means that you can go back to work after the earthquake. Some minor repairs will be done on that. And life safe, the last spalling has not happened, or it has just happened below that only, then it is life safe. And if the first crushing has not happened, then you are not yet collapsed, and so you are within your near collapse condition. This is what we managed to give a quantitative definition of their qualitative statements. So for the international documents. Now, so we are looking at a performance objective. The third item is where the game is. It has to be operational, occupiable, life safe, near collapse. We managed to put them into some quantifiable terms there. Now, what are the other countries are saying? Look at European code, New Zealand, then the British, American, and then the California code. As of now, there is no convergence in what they are saying in different documents. We don't have a performance-based design document. The red one is our regular design document, right? Performance-based design document exists only for the CEOC, the Structural Engineers Association of California. They have a document. There are other research documents here and there on how to do performance-based design, but largely this is the first, this one. On the left-hand side, left of CEOC is all the current design procedures. As you can see, most of them say no collapse, but there is no procedure for examining collapse. And that is why when the earthquakes happen, there are collapses, they get worried again. And so we are saying we need to look at the closed loop method of design is the only way to reduce the number of collapses by catching the error earlier on in our lives. So where do you use performance-based design? In the design of new buildings, in the design of new structures, in the design of non-structural elements, no, you cannot use performance-based design. In the design of in the assessment of existing buildings, in the assessment of existing structures, or if you have designed a new building and you want to learn what will be its behavior, yes, for new buildings, assessing new buildings and new structures also, you'll be able to use that. And likewise, non-structural elements in new buildings, existing buildings, and new structures and existing structures, you can use this procedure to assess the structure. Why this is being stated this way? Because the design procedure is a legal document which is required by the country. But sometimes when those legal documents are not robust enough, then we will have collapses. And that is why we are saying, as a conscious designer, as a conscious structural engineer, geotechnical engineer, please do this reverse loop and assure yourself first and then the client that indeed you have done due diligence to show that there is no collapse happening, right? And available methods, you know that we have linear and non-linear methods and number of methods. You can see that in 1960s, we were using linear static analysis. We couldn't do performance-based design then. 60s, 70s, we're doing linear dynamic. We can't do performance-based design in that. 80s, 90s, we started non-linear static. We got started with performance-based design because we used pushover analysis as a basis when we started. And now today in 2010s and 20s, yes, we are using nonlinear dynamic analysis as a basis to evaluate performance of structures during strong shaking. Okay, what are the inputs to pushover analysis or even nonlinear time history analysis? It is the hinge properties of members under different load actions: axial load, axial deformation, shear force, shear deformation, bending moment and rotation, torsional moment and twist. The nonlinear static pushover analysis or nonlinear dynamic analysis, both of them require this input. So what's the outcome of that? Outcome is capacity curve over which the entire displacement loading. And so we learn how the stiffness and strength are changing along this displacement push. It is useful to understand relative behavior. For example, you have an open ground story structure and a structure without open ground story. How do they behave? Open ground story structure will behave in a brittle manner, and that is what is coming out explicitly here. So two ways of doing pushover: force control, displacement control. And in force control, the force profile is not changed. In displacement control, displacement profile is not changed. It's the same throughout the push. And that is something that is being contested now. So the limitations are higher mode effects are neglected, does not consider dynamic effects, and there's a difficulty in combining earthquake shaking happening from multiple directions, X, Y, and Z directions. Because of this complaint of the or lateral displacement profile being constant, what they have suggested is that every time there is damage, let us modify the displacement profile along with which we will push. And so this is called the adaptive pushover analysis. This is being used in many occasions. So the CEOC book said, come up with the pushover curve and show us your performance points SP1 to SP5. And they have defined if delta P is the maximum displacement, then fractions of delta P is the one that will define all the remaining performance points. This is also not correct. It will depend on the structure, detailing, and so on. But they are saying, no, our structure is designed by our standards. This is the general trend that we are seeing. Fair enough. And so they gave limits for that. And if they are following these limits, then that is the acceptance criteria. So as of now, CEOC document managed to come up with a quantitative way of looking at the performance-based design for the overall displacement check on the structure. Right? Nonlinear dynamic analysis on the other side is similar, but yes, we will use ground motions alongside. So structural model is there, and then you use the ground motions based on the distance of the fault and so on, and then you do a incremental dynamic analysis and come up with the spread of the response backbone curves, and then get the median values for that. And then you go ahead and plot that maximum interstory drift ratio to the residual interstory drift ratio. That will show you here that the probability of exceedance is going to be coming out very clearly, that you are seeing that the maximum interstory drift ratio is higher and residual is lesser. Once the residual gets closer to the interstory drift, then you know that the design is not correct and it is going to collapse. So this is where they are using nonlinear dynamic analysis for evaluation of the performance of the structure, using that performance matrix that I showed you right at the beginning, that frequent earthquakes, occasional earthquakes, and so on, rare earthquakes. So one other important point that we need to remember here in retrofit of structures is that we are looking at cost of the structure. If you put more structure cost initially, then the retrofit cost is lesser. And if you put less cost initially, you will do a large retrofit cost. So on the whole, what it turns out is that for the same cost, you will get two structures, one on the left-hand side to the minimum and one to the right-hand side. The one on the right-hand side has collapses and losses of life, and one on the left-hand side has only damage. So performance-based design is important to quantify what should be the initial design lateral force. So anybody who is trying to go to the right side by reducing the initial design lateral force is actually going towards collapses and losses of life. Wisdom says minimum 30% of the weight of the structure is where you will see no collapses. If you are less than 30%, anything can happen on that. Right? So this is where grave consequences are, and then that should be our focus to go to the left of center. Yeah. So, and then you can fix costs according to that. I'll go to the second section quickly, myths and fallacies. First of all, yesterday I talked about competence having three components, right? And then attitude controls both of them. We talked about what is attitude, what is skill, and what is knowledge. But I'm coming back to myths. Myth is an idea which many people believe, but that does not exist or is false. And fallacy is a false belief or a wrong idea itself. The idea is wrong to begin with in fallacy. In myth, the idea may be okay, but it is not, it is believed by a lot of people, but it doesn't exist. The idea doesn't, it's not realizable, it's not achievable. So it's in one case, it's a false understanding of the behavior of structures. In the other case, that is not a likely situation at all. The myth is not likely at all. So let's look at it. Incomplete knowledge and incomplete skills can lead to a negative attitude. And the negative attitude will lead to myths and fallacies. So all that comes out to be is that if you don't understand the behavior of structures, you will think that this is the final and the ultimate. Whatever you know is correct, and that is where the trouble begins for us. These are the 7 virtues that we talked about, right? And so when you look at uncertainties, where are all the uncertainties? Uncertainties are in earthquake hazard, earthquake analysis, on the demand side, and on the capacity side, earthquake resistant design, earthquake resistant detailing, construction and maintenance. I'll not talk about construction and maintenance today, but I'll quickly touch upon hazard. See, normally there are random loads and non-random loads. Of course, you know all the loads that we have on all sides. The key issue is that we are looking at design loads here, which are supposed to be Poisson distributed in the case of an earthquake. And this distribution has not been obtained for all countries. So exactly we don't know what will be the distribution of the earthquake loading. We have to consider this in seismic hazard assessment. Only then we can say that we have done it properly. By merely setting a value of 0.36 G, we don't do seismic hazard assessment. So the Andaman Nicobar Islands, the west coast of Gujarat, the Himalayan belt are all having one special feature that means that there is a slip that is happening, which is going to give you fault parallel actions, which are residual slip, and fault normal actions with no residual slip, but large velocities, right? And these have to be recognized in our seismic hazard assessment. As of now, Indian standard does not do that. Also, there's a large sediment in the northern part of India and the Indo-Gangetic plains, and that sediment is not considered in the analysis when the earthquake is happening under the Himalayas. How does it travel through these sediments is the key question. And this is the Indo-Gangetic plain. Those of you who are in Gujarat will definitely understand that you are sitting on Indo-Gangetic plains and this is the collision of the Indian plate coming and hitting the Eurasian plate, and this is the ocean bottom material, sandy material, soft sandy material that has got uplifted, ocean bottom material that's got uplifted. On modeling side, hinge properties have not been properly incorporated yet. We did not do enough experiments in India to come up with the correct hinge properties. Also, we didn't do enough experiments on using idealized hysteresis rules. We didn't manage to quantify those rules properly to mimic the actual behavior of the structure. Another big issue that stands is that the earthquake shaking causes cracking, and that cracking leads to loss of moment of inertia. So we don't know which moment of inertia to be used during earthquake shaking. For example, if that's the backbone curve that we were looking at, and look at the moment of inertia, once nonlinearity begins, moment of inertia drops and even goes negative. Now, how do you take negative moment of inertia? That is the worry that we have, is that this is the biggest question that we have is how do we handle this negative moment of inertia and negative stiffness that is happening on the falling part of the backbone curve. We are taking the first mode as pushover analysis, and in nonlinear behavior you cannot combine the modes. So neglecting rotations and considering rotations will make a big difference. Considering first mode alone and other modes will make a big difference. Without accruing damage and with accruing damage, the mode combinations are going to give us completely different results. And that is where the game is, that in earthquake resistant design, when you look at it, PVM interaction is one area where we haven't done any work in the country and we're doing design independently. We only have a PM interaction to begin with, but the shear coming into picture in earthquake is all about shear, and large shear means we will have significantly reduced moment capacity and axial force capacity. This is not reflected yet in our standards, right? In detailing, we don't know how to model 90-degree hooks when you come to the nonlinear behavior of structures. And so that is an open area, and most of our structures are 90-degree hook ends. And so how do we really model those? It's not clear to us. So earthquake shaking imposes displacement loading under the structure, and if you have this displacement understood properly, then only you'll be able to say that the structure is safe. In fact, the 2 questions that I asked are related to this, that strength implies safety. That is not correct. because it is deformation that controls earthquake safety, and so strength does not imply safety in this case. Another is that structure goes into inelastic action, so the elastic response spectrum that we are using becomes irrelevant at some point of time when ductility comes in and damage comes in, then the spectrum shape itself changes and becomes highly nonlinear. And this has not been reflected in our standards yet. So another important issue is that for there is long period structures, we are seeing that equal displacement rule is applicable, and that is how we are estimating the maximum displacement. And for short period structures, equal energy rule is to be used for short period structures. What has been said is in both cases, they have observed when they did time history analysis that unconservative estimates were obtained for displacement. That means if you're saying that the equal energy will work for short period, it's not working. And if you say equal displacement works for short period, long period, that is also not working. So in the road ahead, what are we supposed to do? We started with intuitive design and currently we are at prescriptive design. We are going towards performance-based design, and road ahead there is risk-based design and finally resilience-based design. So in the intuitive design, we were working on concepts of structural behavior and the concepts held by the designers. If they have poor concepts, then gone. And in prescriptive design, concepts plus structural safety standards. In performance-based design, that plus functional expectations by owners. In risk-based design, plus life safety and retrofitting expectations by community. And in resilience-based, downtime, livelihoods, restoring livelihoods, and business and governance continuity by governments. So you can see from designer to standards to owners to community to governments, a lot of expectation is going to come on structural engineers, and we just can't stay at the prescriptive design level. We have to go past and learn more about the newer methods of design so that we'll be able to answer the tough questions. One of the questions is under normal wind load itself, the performance is not acceptable in many buildings. And talking about earthquake load, they are not able to take so much of retrofitting cost, how to make sure that that is reduced. And finally, governments are saying, no, this resilience is important for us. We have to make sure that there is resilience in the built environment. Just the structural safety alone, if you look at that part, there are 7 activities: stability, stiffness, strength, ductility, deformability, energy, dissipation, and motion. We have not managed to answer all these questions yet, right? We're just at the first 4 levels, and in that itself, we are having difficulty. 5, 6, 7 is yet to come for us. So we have a long route, and if you look at way we are conducting ourselves, we do analysis on the bare frame and we design on the bare frame and we do pushover analysis. We get great curve, large ductility, but when we construct open ground story, we get higher strength but no ductility, and the buildings fall suddenly. And earthquake is displacement loading. There's not enough deformation capacity, and so structure collapses. Therefore, bottom line is that 3 things: behavior, design, and analysis are related to each other and alongside construction. Now, we need to design to control the behavior, and we need to analyze to reflect the behavior. But analysis is to be done on the designed and constructed structure, and you need to design that structure which is analyzed. So these are all related to each other, and we need to be very careful in trying to do earthquake resistant design. It is not rocket science, but it's a lot of bookkeeping. It's just discipline of the mind. I'll stop here by saying that once again, earthquake engineering is art in engineering, and all the tenets are in keeping with us, and we are hoping that we will be able to make progress in here. I'll stop here by thanking Colonel Saab to bring me here and the opportunity to speak on the subject. Jai Hind. If you have any questions, I can take them now.
Thank you so much for such an intellectual and informative session. This would have surely benefited all the participants in enhancing their knowledge on the concept of myth and fallacies of performance-based design. Each and every concept was touched in a well-organized way, which helped every participant to have a crystal clear understanding of various topics like structural behavior, quantitative assessment, displacement and performance-based design, design philosophy, method of analysis, structural safety, and many more. Thank you so much, sir, for giving us your valuable time. Now, sir, with your permission, can we open question answers round?
Yeah.
So those who have any questions can raise their hand. We will unmute you.
There's one hand by Yogesh Chauhan. Yogesh Chauhan, can you switch on your video? Yogesh Chauhan, can you switch on your video? Yogesh, you're muted. You're muted. Yes, Yogesh. Can't hear you, Yogesh. Breakfast नहीं खाया. Voice नहीं आ रहा है. What happened to all the 2 million lunches, breakfast, tea, dinners that we had? याद करो उन शहीदों को.
You can just check your audio. No, still not audible.
Okay, Yogesh, you type your question. Yogesh, you type your question. In the meantime, let us look at the others. आप चैट बॉक्स में क्वेश्चन टाइप कर सकते हैं? चैट बॉक्स है नहीं है यहाँ पे?
है सर, है सर.
है ना?
हाँ है सर.
एक मिनट.
Because if you rejoin, then I think audio problem will be solved.
Unmute yourself, Yogesh, once more. Okay, anybody else?
Sir,
Sir,
myself,
Lokesh.
Vinayaka, sir.
Lokesh is another next question. Lokesh, go ahead, ask your question and we'll wait for Yogesh to improve his audio.
Yes, sir. You were telling about the different waves, P waves, S waves, love waves. Are there different techniques to face these different waves? Or is there any particular factor that will contradict among the way in which we face these different waves? Or the same factors apply for all waves?
See, you as an engineer will not see the difference. They'll all come in a combination.
Okay, sir.
Love waves and Rayleigh waves are on the surface, P and S are on the body also. Right? Now, P and S come with lot of energy and they will hit the site, let us say Chennai city. They're coming from Andaman Nicobar. So what happens is, for us, the net combination, you will be able to see two dominant motions. One is a very gentle motion and suddenly it will start shaking vigorously. These two are called arrival of P and arrival of S. But as engineers, we are not so much worried about these. Okay. It is quantified in the design spectrum itself.
Okay, sir.
Our main worry is the severity of shaking that comes in, the velocity of reversal of the ground, the acceleration of the ground. Those have to be accounted for in design. And through design response spectrum, through recorded ground motions, we don't have a station in Madras city which is recording strong ground motion. Do we have? The headquarters of every city and the capital of every state is supposed to have. So let us go to IMD in the city and ask them to give us the record of the Andaman Nicobar shaking. You can use that in the classroom for your students' work.
Yes, thank you, sir.
Okay. Okay, is Yogesh back? Yogesh, don't be shy. Please speak. अरे I learnt when I was younger, नाम गुम जाएगा, चेहरा बदल जाएगा, मेरी आवाज ही पहचान लो. आज तो आवाज ही नहीं आ रही है. नाम और दिख रहा है, चेहरा दिख रहा है, लेकिन आवाज नहीं आ रही है. टाइप करो भाई, टाइप करो. ऐसे नहीं चलेगा.
Yogesh, type your question, please.
Type your question. Anybody else wants to raise a thought?
Bharati sir has raised his hand.
Yogesh Chauhan is the only one. Lokesh finished. Anybody else? Bharti sab. Bharti sab.
हाँ, shall I?
Yeah, please.
Shall I speak or I'll let others also speak first, then I can speak towards the end?
They are returning their salaries today. At least you get your salary home.
So I was just wondering when I look at the literature, I mean, so-called research literature or documents available all over the world, particularly the West, the America, about performance-based design. I wish if you can, I mean, make a slide or generally just like that, what it is not. Sometimes it so happen that saying that this is what it is, it helps. But what it is not will also, create a contrast. So towards the, maybe in the next half, you can.
No, for example, one slide that I showed, that it is not meant for design of new structures.
Yes,
definitely
so it's an assessment. It's an assessment.
It's an assessment tool as of now. The reason is that without any basic benchmarks, no country can say that I will design at my own will and fancy and allow people to come and go inside and have buildings by its side. And if anything happens untoward, it is not as per the law of the land.
Yes. So what it is not को लेके 5-6 point हो सकते हैं, मुझे लगता है.
We can elaborate on that. We can elaborate on that.
Yes. I mean, neti. This is not. This is not. This is not. This is not. So that helps actually.
Yes.
नहीं तो घूम फिर के क्या होता है कि performance based design somehow I mean when you say myth means it has become a belief which is governed by cult feeling. I mean it's not based on some verifiable solid facts.
For example, I did say that they have stated the framework background of it, but they have not quantified any of it carefully. See, for example, they're saying that performance-based design should be used for the purposes of deciding cost. How do you relate cost? Every project is so unique, so that is not happening. Then they said performance-based design should be based on comfort of the people staying in that. Now, earthquake oscillations are so violent, and if your non-structurals are falling on you, how do you control the issue of vibrations, perception of vibrations? Let's try with Yogesh Chauhan. Yogesh.
Yes, sir. Am I audible now?
Now you're audible. Yes. Congratulations.
Yeah.
Your voice has come back.
Your voice is back.
So you discussed various categories of the building: normal, important, critical, special, and NPPs. In critical, the transport gas, they were categorized as critical. Why they are considered more important than important buildings like hospitals?
Yeah. See, what happens is hospital requires ambulances to come and bring patients.
Yes.
So if there are no bridges, how will hospitals run? If you say hospital is more important than the bridge, and in Himalayan region, if the ambulance is not able to come, what is the point? I'll sit, watch. Doctors will play cards, watching. No ambulance will come if bridges fall down. If there's no water in the hospital, if there's no gas in the hospital, if there's no electricity in the hospital. So these are called lifeline systems, critical and lifeline systems. So lifeline systems are much higher level because it is required for the entire community. Right? Because hospitals are concerned, they're very crucial for us, very crucial, no doubt about it. Right? But the fact is that there are distributed number of units, hospitals. But the lifelines are not like that, only one, no redundancy. The water supply pipe from municipality to your house is only one pipe. There are no 3-4 pipes. In hospitals, in the same street, we can have 3-4 hospitals. That is the game.
And which type of structures are categorized under special category? Which
Special category, see, what happens is there are a set of structures where we cannot, they are confidential structures. So we don't want to declare all of those, and they are put in the special category. Or for example, our, Dhirubhai Ambani can decide that, no, my plant is special. I want to design for higher level. Individual, I can afford to pay, so I will make a special. So the owner can decide which level you want to design your structure. Owner can decide.
Okay.
And the last one is, yes, who is this? Deepa Rawal.
Yes, sir.
Sir. Yogesh, you have any question or you're done?
Yeah, done, sir.
Okay, lower your hand. Deepa Rawal.
Yes, sir, yes, sir. Sir, the doubt is one way of assessing the performance is push over
मैडम आपका वॉइस
थोड़ा
ब्रेक हो रहा है, आपका वॉइस ब्रेक हो रहा है.
Okay, sir. Am I audible properly now?
Now you are audible.
Okay. Sir, one way of assessing the performance is pushover methodology, which analyzes under the push effect, what are the critical forces. Is there any other way of assessing the performance? Because it may so happen that in some different type of structure, the vibrations go in a resonance mode or the response.
Yeah. So is it? So I did show the second method also. It is called the nonlinear time history analysis method, and in which you are going to take a building, model that building, and put earthquake shaking, ground motion underneath, and do a nonlinear time history analysis. And that is called the incremental dynamic analysis, where the time history, the shaking below is slowly, intensity of that is increased, and then you will see the performance of the structure at different levels of intensity. Both are done. First, you do the pushover to get a basic understanding, and you realize that the building is twisting too much and so on. It's a bad structure. Then you go to dynamic nonlinear time history analysis and show that it is indeed very bad and its performance is not acceptable. Even if it is showing good behavior under pushover, you will notice that sometimes under nonlinear time history analysis, the strength matters come into picture, and you will get some nonlinear behavior under time history actions which are not desirable. So you can even declare a structure to be of poor quality if nonlinear time history analysis is able to show you that one. Nice. Lokesh is back. Thank you, ma'am. Lokesh is back.
Sir, you were talking about some analysis softwares. Could you recommend us some good softwares which we could refer to, sir?
Officially, I'm not supposed to be working for any company.
Okay, sir.
Do some hard work or come to my office, I'll tell you directly.
Yes, sir, sure.
No emails also, because emails will fly.
Yes, sir.
And if you come to my office, keep your phone outside, all of those recording devices outside.
Yes, sir, I'll surely contact
you. No pen mics and pen cameras, no.
Yeah. Yes, sir, I'll contact you.
No, it's a public secret. It's not something there are 5, 6, 7 types of software that are going around here in the country. And you can choose, depending on your pocket, you can choose any one of them. And if you surf the net, you will get immediately 5, 6.
Yes, sir. Thank you, sir.
Okay, there are 2 hands. Lokesh is done. Deepa Rawalji is done. Okay, looks like there are no more hands. We can take a short break and come back at 12.
Yes, sir. It's fine.
Thank you, sir. Thank you, sir, for answering all the.
Yes, Chetan bhai.
Yeah. Sir, I want to ask you how your presentation is so lucid. Is it how you prepare that? because it is quite penetrative and we can understand very easily. And I think you a lot of like your presentation is really wonderful. हमें मतलब उससे ही ज्यादा पता चलता है, मतलब आप जो एफर्ट करते हैं प्रेजेंटेशन में, ये जो पिक्चर्स और सब,
we have to do a lot of menial work. We have to do a lot of menial work. Anybody who thinks that drawing a picture is below my dignity and that a draftsman will do the drawing, then you are not conveying your idea. Draftsman doesn't know your idea. Because we are taught this engineering drawing in our childhood to draw these pictures only to tell others how to understand a certain aspect of structural behavior. So it takes time. It's no magic here. There's no any extra issue. Just you have to spend time. And of course, you are doing the right brain in choosing the right colors and combination. That's all. And then you have to keep watching for these pictures, the wonderful pictures on the backdrop, and then bring them in.
You are doing on your own, sir. That is the
I'm my own peon. I'm my own typist. I'm my own teaching assistant. I'm faculty member. Everybody, all in one.
Right. Yeah, sir, it was really wonderful, sir. I think as far as this performance design is concerned, I think lots of doubts have been clear. So,
Ji. Chalo, thank you. So we'll come back at 12 and talk of technology.
12 o'clock.
Yes, sir. Yes, sir. Yes, yes, sir.
Thank you.
Thank you.